A measure of location or an average gives us information about just one characteristic of a distribution. And that's fine if your distribution looks like this one in the top panel here, where all of the observations are concentrated in a spike. It's not so great if your distribution looks like this, though, in the bottom panel, where though many of the observations are concentrated in the middle, there is a significant spread to each side. It would be nice to know something about how observations are spread out, in other words, their dispersion. Just as there are a number of measures of location, there are also a number of measures of dispersion. We'll look at the principal ones in turn. First of all, the range. The range is the difference between the largest and the smallest observed value, the maximum minus the minimum. For the 160 countries in the Demography dataset that we've already looked at, the range in per capita GDP is $92,700. We get that number by subtracting the smallest value that we observe from the largest value. So we subtract $700 from $93,400, which is the highest observed per capita GDP, and that gives us the answer 92,700. There are some disadvantages of the range, and they're really quite obvious. Firstly, it ignores most of the observations, so we're only using a very limited amount of information. Secondly, it's sensitive to extreme values. Thirdly, it's sensitive to the size of the sample. The larger the sample size is, it gives us more opportunity for more extreme values to be observed. Next up are the quartiles. The lower quartile is the value such that 25% of the observations are smaller than or equal to it. The upper quartile is the value such that 25% of the observations in your distribution are bigger than or equal to it. The middle quartile is just another name for the median. All of these are a subset of a larger set of statistics called percentiles. The 5th percentile, the 95th percentile, and so on and so forth. The median is the 50th percentile. One important thing to note, quartiles are only unambiguously defined for a continuous distribution. You could read the quartiles off a cumulative relative frequency plot, such as the one that I'm showing you here. But it's probably better to just ask R to calculate them for you. Recall that if the sample size n is even, we need to invent a procedure to identify the median. Something similar, for example linear interpolation, can be the case for the lower quartile and the upper quartile. But for our purposes, it's not necessary to go into all of that. Next up is the interquartile range. This is the difference between the upper and the lower quartile. In the previous slide, I showed you a cumulative relative frequency plot for GDP per capita for 160 countries. For those data, the interquartile range is $23,400. As it only uses the middle 50% of the distribution, the effects of extreme values in the tails of the distribution are effectively eliminated. This is of course very useful when there are outliers, in other words very extreme values, or when the distribution is very skewed. You might sometimes see reference to the quartile deviation or semi-interquartile range. The quartile deviation is the interquartile range divided by 2. All of the measures that we've looked at so far basically work by ignoring part of the data, by essentially throwing away some of the observations. But what about something that uses all of the observations? Okay, so I want to proceed by initially thinking about this example. Here's a little data set. It is about height, the height of 6 12-month-old children, measured in centimetres. Here they are here. This is the first child, second child, all the way through to the 6th child. These are the sample members. In this column here, we have their heights. They range from 62 centimetres through to 72 centimetres. Okay, so what could we do with this data? Well, first of all, maybe we might calculate the mean. Of course, that's not going to tell us about dispersion, but we might make use of that later on. Okay, so what do? Well, we sum all of these numbers up. If we sum these numbers up, it gives us 408. And then if we divide 408 by 6, the total number of sample members, then we get 68. 68 is the mean of this distribution. Okay, so far, so good. What might we do next? Well, we might look at the difference between each observation and the mean. In other words, subtract from the observation the mean value. So for the first one here, 62, we would subtract 68 and get minus 6. For the second one, 66, subtract 68 and get minus 2, and so on. This gives us a measure of deviations around the mean. Is that going to help us? Perhaps not. Because if we sum all of these up in the hope of getting a single number summary measure, what are we going to get? We are going to get 0. Why 0? Because the positive deviations, by definition, are equal to the negative deviations. So that's not going to work. Righty-ho. What about the third column here? Here's a better idea. Why don't we just ignore the signs here? In other words, why don't we just consider the absolute value of the deviation? So if we've got a negative sign here, we just take it away so all of these end up as positive numbers. If we do that and add them all up, sum them, we get 16. And if we divide it by n, the sample size, 16 divided by 6 is 8 over 3, which is approximately equal to 2.67. So 2.67 is clearly some kind of measure of dispersion. Might we do something else? Well, the obvious move might be to square the deviations. If we square these deviations, we will again end up just with positive numbers. Minus 6 times minus 6 is 36, just as 6 times 6 is. So if we do that for all of these observations here, what are we going to get? We're going to get the numbers in this column here, sum them all up, it's equal to 64, divide by 6, which is 32 over 3, and we get a number which is, again, roughly 10.67. This, again, is some kind of measure of dispersion. Okay, let's think about all this in a little bit more detail. So we've seen that subtracting the mean from all of the observations and summing them doesn't really give us anything terribly useful, because that sum is always equal to 0. We've also seen that if we ignore the sign and sum the absolute deviations, we get something that looks rather promising, and something that captures the dispersion around the mean. What we've done is reinvented something called the mean deviation. The mean deviation, to calculate it, involves summing the absolute value of all of the observations minus the sample mean, and dividing that sum by n. So for each observation, we subtract from it the sample mean, take the absolute value, do that for each of the observations, sum them, and divide them by the sample size. In this case, as we've seen before, the MD, as it's sometimes called, or even more attractively, MAD, M-A-D, is approximately equal to 2.7. The mean deviation had some influential advocates, among them the astronomer Arthur Eddington. It is a perfectly sensible measure of dispersion. We can also add a twist to it. We can use, instead of deviations around the mean, deviations around the median, and this is particularly useful when the distribution is long-tailed. In fact, it turns out that if we do this, in general, this minimizes the mean deviation. But, and this is a very big but, there are some mathematical difficulties in building a body of elegant statistical theory around the mean deviation. I want to turn now to the standard deviation. Now, this idea has a very long history, but the term standard deviation, though not the idea itself, was introduced by Carl Pearson in 1893, and later on rather vigorously championed by another famous statistician, Ronald Fisher. We're already, in our example, about 90% of the way to defining it. What are we going to do? Well, the idea is square all the deviations between the observed value and the mean, add them up, and then divide this sum by either n-1 if we're working with a sample, or n if we are working with the population. Notice that we have to make a decision. Are we working with a sample from a population, or are we working with the population itself? And I'll say a little bit more about why this difference. If we do this, the result will be in units of squared centimetres, which is a little bit odd. We can of course then easily return the measure to its original scale by simply taking a square root, and if we do that, we have the standard deviation. Let's think about this a little more. Before taking the square root in the last step, we have essentially this expression here. Now, by convention, we denote this using the symbols s squared. S squared stands for the sample variance. Just to recap, we are subtracting the mean, the sample mean, from each of our observed values. We're squaring them, and then we're summing all of those squared deviations up. And then, because it's a sample, we're dividing by n-1. This clearly captures the idea of an average squared deviation from the mean, which tells us something about the degree of dispersion. Now, in the final step, just take the square root. What we've got is the sample standard deviation. It's by convention denoted by small Roman s. We've got the sample deviation, and it's expressed in whatever the original units were. That is the effect of taking the square root. Note, by the way, that we've given more weight in the sum to observations that are far from the mean. Obviously, deviations from observation values which are close to the mean, when they're squared, are relatively small, and deviations which are rather large, indicating that the observation is quite far from the mean, once we square them, those are going to get rather large. But why the sample size, small n, minus 1? Well, big N, the population size, would be fine if we are dealing with the population variance, or the population standard deviation, notice that by convention the population variance is denoted small Greek sigma squared and the population standard deviation by small Greek sigma. When we're working with population data and we want to calculate the population variance or the population standard deviation, the population mean will be known rather than estimated. It has to be, because we couldn't calculate the population variance or the population standard deviation if we didn't know the population mean. When we look at the deviations between each observed value and the mean, that assumes that we know what the population mean actually is. Now, returning to our question, why n-1 in a sample? Well, first of all, let's take a step back. When we're looking at sample data, we're normally looking at sample data because we want to make an inference about a population value. Okay, so here's the first of the two possible answers, a short one. It's been shown that dividing by the sample size -1 eliminates bias in the estimation of the population variance and reduces it in the estimation of the population standard deviation. And for the purposes of this course, that's all that you need to know. Okay, here's the second explanation. Notice, by the way, that the colour of the slide has changed. When I give you additional information that it's not really that important to follow, and certainly won't be anything that you're going to be examined on, I make the background of the slides green. This is really just a kind of thing for people who are interested in a slightly deeper explanation. Okay, recall that we want to use the sample variance, small s squared, to estimate the population variance, Greek sigma squared. Ideally, we would like the sum of squared deviations to be around the population mean. By convention, the population mean is usually denoted as Greek mu, small Greek mu. Okay, if we use the population mean and calculate the sum of squared deviations, we would be basically doing this, summating for each of the observations in the sample the difference between itself and the population mean, squaring them. But of course, normally we don't actually know the population mean. In fact, one of the reasons that we took a sample in the first place was probably to estimate it. Well, we don't really have too many choices. We're going to be forced to use the sample mean, which is an estimate. So instead here of using the population mean, small Greek mu, we use the sample mean in order to calculate the deviations, the squared deviations that are going to be summed. Well, that seems somewhat reasonable. However, recall that we said before that the value of the mean can be thought of as the number which minimizes this summation here. The mean is the value that minimizes the sum of the squared differences between itself and the values of the observations. But that means that for any sample data that we might have, the following relationship applies. The sum of squared deviations in the sample around a known population mean is always going to be greater or equal to the sum of squared deviations around the sample mean calculated from the sample. the sum of squares around the population mean will be larger than the sum of squares around the sample mean, unless by some miracle the sample mean is exactly equal to the population mean. From that it follows that the estimate of the sum of squares that we get from a sample will normally be too small, which means if we divide by n, the estimate of the variance will systematically be too small. It's been shown, initially by the German astronomer Friedrich Bessel, that dividing the sample sum of squares by the sample size minus 1, rather than just by n, the sample size, gives an unbiased estimate of the population variance, which is truly great to know. But as the sample size n gets larger, the difference between dividing by n and dividing by n minus 1 gets smaller. In fact, in most applied work with a reasonably large sample, the difference will be negligible. So in fact, in practice, whether you divide by n minus 1 or n probably will make very little difference. So here's the bottom line. This is really all that you need to know for this course. If you're dealing with population data and you want to calculate the variance and the standard deviation, divide the squared deviations by the population size, big N. And if you're dealing with sample data from a population and you want to calculate the variance in the sample and the variance and the standard deviation in the sample in order to estimate the population variance or the population standard deviation, then you divide the squared deviations in the sample by small n minus 1, the sample size minus 1. Just to fix ideas, let's go through one final example. Here we're going to calculate the standard deviation, and in fact the variance as well, of the number of hours worked on Sunday by a sample of 5 department store employees. Here they are here, employee 1, 2, 3, 4 and 5. And in this column here, these are the observations, these are the observed hours that they work. Individual number 1 works 5 hours, number 2 4.5 hours, number 3 6 hours, and so on. Okay, so what do we do first? The first thing that we do is sum all of these numbers up. If we sum all of these up, they total to 25. If we divide 25 by 5, 5 is the number of observations that we've got in the sample, it equals, rather obviously, 5. 5 is the mean of the sample. Next step, calculate the deviations from the sample mean. 5 minus 5 is 0. 4.5 minus 5 is minus 0.5. 6 minus 5 is 1, and so on. So now we have the mean deviations. In the last column, we square all of these mean deviations. 0 squared is 0, minus 0.5 squared is 0.25, and so on. Next step, sum all of these numbers here. If we add them all up, we get 4.5. This is the sum of squared deviations around the sample mean. Okay, next step, we divide 4.5, the sum of squared deviations, by, in this case, 5 minus 1. Why 5 minus 1? Because we're dealing with a sample, so we need to divide by small n minus 1 if we're going to get an unbiased estimate of the population variance. That gives us the variance. The variance in this case is 1.125. This is a measure of dispersion. This measure of dispersion is in squared units. That's not really so helpful, so we return it to the original units, hours rather than squared hours, by taking the square root. If we take the square root of the sample variance, we get the sample standard deviation, which in this case is 1.061. Toy examples are very nice for working out the details of calculations. But of course it's also nice to see some real-world examples. Here's an example. It's of the use of the standard deviation to track convergence in the growth rates of economies. The data come from the World Bank, and what we have is the standard deviation of GDP growth in 122 countries between 1978 and 2020. The basic underlying data is for each country we have their GDP growth rate in a particular year, and for each year we calculate the standard deviation. So what we're really looking at is year on year whether countries become more similar to each other, the distribution of growth rates is compressed, or whether they become more different from each other, the dispersion gets wider. As you can see in the graph, the general trend over time, despite quite a lot of quite erratic fluctuation, is for countries to become somewhat more similar. That is until we get to 2020, probably actually 2019, when things change quite dramatically because of the effects of COVID. Okay, here's another example. In fact, it's one that we've seen before. It concerns the height of females 20 and over in England in 2019. Have a look at the distribution. It looks relatively symmetrical. That implies that the mean and the median are probably going to be quite close together. And if we calculate the mean and the median, we see that that's the case. The mean is 161.4 centimetres, the median 161.5. So very close to each other indeed. Turning to the dispersion, the interquartile range is 9 centimetres. Half of that gives us the quartile range, 4.5 centimetres. The mean absolute deviation is 6.8 centimetres using the mean and 6.7 centimetres using the median. Again, these are very close to each other, which is what we would expect simply on the basis that the mean and the median are close to each other. The variance is 47.4 centimetres squared. Centimetres squared is a rather horrible metric for height. We'd really like to return it to a more natural metric, so we take the square root. That gives us the standard deviation, which in this case is 6.9 centimetres. Because the distribution is symmetrical, we actually get quite a good idea of what it looks like simply from the knowledge of the mean and the standard deviation. Symmetry plus knowing the location in terms of the mean and knowing the dispersion in terms of the standard deviation really gives us a pretty good idea of what this distribution is like. There are some properties of the standard deviation that it's useful to remember. If we add a constant to every observation in a data set, then the standard deviation doesn't change. Adding a constant to each observation also adds a constant to the mean, so doesn't affect the deviation from the mean. If we take this set of observations here, 1, 2, 3, 4, 5, and calculate their standard deviation, it will be the same as the standard deviation of this set of observations here, which is this set plus 100. Now, this is fine for talking about dispersion. It's less convenient if one wants to talk about inequality. For example, imagine this is a society in which this is the dollar wages of a sample of inhabitants, and this is another society in which this is the dollar wages of the inhabitants. Is it really true that this society here has the same degree of inequality as this society here? The dispersion might be the same as measured by the standard deviation, but it would seem quite odd to say that this society here is as equal as this society here. If we multiply every observation, either in a sample or in a population, by a constant with a value of k, then the standard deviation is also multiplied by k. So the standard deviation of 1, 2, 3, 4, 5 is approximately 1.58, and the standard deviation of 1, 2, 3, 4, 5 multiplied by 2, in other words 2, 4, 6, 8, 10, is twice 1.581. The standard deviation of the first set of numbers multiplied by 2. So the units of measurement really matter. If we measure income in cents, we'll get a different value for the standard deviation than if we measure them in dollars. Sometimes this is put as saying that the standard deviation is not scale invariant. We can make the standard deviation scale invariant by dividing it by the mean. This is called mean standardization. The mean standardized standard deviation is usually called the coefficient of variation, or CV for short. For a sample, it's the sample standard deviation divided by the sample mean, small s over x bar. For a population, it's the population standard deviation, small Greek sigma, over Greek mu, the population mean. For the coefficient of variation to make sense, the observations have to be measured on the ratio scale. They have to have a non-arbitrary 0 point. Otherwise, taking the ratio makes no sense. Here's a little numerical example to show you that this really works. Here's a set of numbers, set of observations, 1, 2, 3, 4, 5. The standard deviation of these is 1.581. The mean is equal to 3. The coefficient of variation is roughly equal to 0.527. Let's multiply these observations by 4. That gives us the set below, 4, 8, 12, 16, 20. Okay, so the standard deviation is going to be 4 times 1.581, which is equal to 6.324. The mean of these observations is 12. If we divide 6.325 by 12, we get the coefficient of variation, which is approximately 0.527. So the coefficient of variation for both of these sets of numbers is basically the same. One practical use of the coefficient of variation is to compare variables which are measured in different units. Here's an example from the Health Survey for England 2019. We have a sample of 3,508 women aged 20 or over. And we want to ask ourselves, is their height or is their weight more variable? We calculate the mean and the standard deviation for each, but this doesn't really help us very much because the units are different. For height, it's in centimetres, and in weight, it's in kilograms. Is a standard deviation measured in centimetres for 6.873? Does that indicate more variability or less variability than a standard deviation measured in kilograms of 17.0? So the trick is to divide each of these by their mean to get the coefficient of variation. Then we can answer the question, is height or weight more variable? The coefficient of variation for height is approximately 0.043 and for weight is approximately 0.233. So we would conclude that weight is somewhat more variable. There's more dispersion in the weights than there is in the heights.